Optimization problems are an application of maximum minimum problems. So we have a quantity that we want to optimize, and usually the optimized value occurs either at a maximum or a minimum. All right, so let's see how this works. Let's look at number one. In number one, it says the product of two positive numbers is 120. Maximize 4 times the first number plus 3 times the second. So let's say our two numbers are x and y, and let's say we have that x times y is equal to 120. All right, so that's that first sentence. The product of two positive numbers is 120. We want to maximize 4 times the first number plus 3 times the second. So let's say q is the quantity that we want to maximize, and q is equal to 4 times the first number plus 3 times the second. So what we want to do is we want to differentiate q, but first we're going to eliminate the extra variable. See, q is equal to a quantity in terms of x and y, and we're going to use this is what's called the constraint, or this first piece of information to eliminate either x or y. Let's say y. So if we want to eliminate y, we're going to solve, and we'll write y is equal to, solve for y is equal to 120 over x. So the first step is eliminate, and so that we only have one variable on the right. So that would be 4x plus 3 times 120 over x. So that's 4x plus 360 over x. So that's the eliminate step. Let's do the differentiate step. So we're just taking the derivative of q with respect to x. So that would be 4 minus 360 over x squared. Remember that the derivative of 1 over x is minus 1 over x squared. Now, in order to find the x value where this achieves a maximum, we're going to set this equal to 0 and solve, find a critical value. So we have 4 is equal to 360 over x squared. Just cross multiply, and we have 4x squared is equal to 360, and let's divide by 4. And we have x squared is equal to 90, and x is equal to the square root of 90. Remember that x and y are both positive, so I didn't write the plus minus square root. We can just simplify this. This is 90 is 9 times 10, so we can simplify that. That becomes 3 square root 10. And now let's figure out what y is. Okay, y is 120 over x, so y is equal to 120 over 3 times the square root of 10. All right, let's just divide 3 into 120. So we have 40 over the square root of 10. Okay, now we want to find the point on curve y equals square root x that is closest to the point 40. So here I drew a picture of y equals square root x. And here's 40 on the x-axis. And I just drew this dotted line and the point xy, and I'm supposing that that's the point closest to 40. And I wrote this variable, I'm using this variable d for the distance between xy and 40. Okay, so we want to minimize d. So first we need an expression for d. Well, we'll use the distance formula for the distance between those 2 points. So that'll be x minus 4 squared underneath the square root and y minus 0 squared. So that's equal to the square root of x minus 4 squared plus y squared. And now we'd like to eliminate either x or y. Well, we didn't use the fact that y is equal to square root x, so we can just substitute that in. For y, we're going to substitute in square root x. Notice it's squared, so we get d is equal to the square root x minus 4 squared plus square root of x squared, so that would be just plus x. So now we're ready to differentiate, so let's do that. So we have d prime. We're going to use a chain rule here. This is parentheses 1/2 instead of square root. We can imagine it's parentheses 1/2. So we'll bring down the 1/2. Multiply to, minus 1/2 here. Multiply by the derivative of what's inside. So we have 2x minus 4 plus 1. All right, so let's write this as a quotient. So in the denominator, we have 2 times the square root, x minus 4 squared plus x. In the numerator, we have, let's just multiply this out. This is 2x minus 8 plus 1. That's 2x minus 7. And we want to know, we're minimizing, where is this equal to 0? Well, we can just set the numerator equal to 0. 2x minus 7 equals 0. So 2x is equal to 7, and x is equal to 7 over 2, or 3.5. And from our graph, that looks correct. The way we approximated this, it looked like x was to the left, a little bit to the left of 4. So from the graph, this does look reasonable. In number 3, we have an open top box created by folding a 12 by 12 in piece of cardboard with 4 equal-sized squares cut out of the corners. So here we have the squares. These are cut out. And these, let's say, are x by x. Each side is length 12. And what we want to do is we want to maximize the volume of this box. So we want to know how large these squares should be in order to maximize the volume. So let's write down an equation for the volume. So the volume is equal to, well, first the dimensions, multiply the 2 dimensions of the base times the height, which is x. When this is folded up, that becomes the height of the box. Okay, let's see. This dotted line would be 12 subtract 2x, so 12 minus 2x. And the same for the other as well. So the volume is x for that height times 12 minus 2x times 12 minus 2x. Now let's factor out a 2 from the first set of parentheses, and then we get 6 minus x, and from the second set as well. So this is equal to 4x, 6 minus x times 6 minus x. Now let's multiply out the 6 minus x times 6 minus x, and so we have 36 minus 12x plus x squared. All right, so v is equal to 4 times x squared minus, multiplying through by x, so here I have x cubed minus 12x squared plus 36x. All right, we're ready to take the derivative. Notice in this one we did not have to eliminate an extra variable. We only had one variable to start with. So now let's do the differentiate step. Differentiate and set equal to 0. So the derivative is equal to, just keep the 4 there. Here we have 3x squared minus 24x plus 36. All right, we can factor out a 3. So let's do that. So we have 4 times 3, x squared minus 8x plus 12. And let's see, when is this equal to 0? Okay, so let's see, we have a 12 there. Well, it's equal to 0. Let's just factor this. and we have x minus 6 and x minus 2. So we have these two solutions, x equals 6 and x equals 2. But we notice that x equals 6 actually gives us a minimum, because that would cut out the entire box. X equals 6 would be squares that are actually equal to 1/4 of this piece of cardboard. So there would be nothing left if we cut out squares of size 6 by 6. So that's not it. So this is the maximum. That one actually is a minimum. This is the max. In number 4, we want to maximize the area of the rectangle that can be inscribed in a triangle whose sides are the x and y axes and the line segment from 0, 4 to 2, 0. So here's a picture. Here's the red rectangle is what we want to maximize. And this is the triangle whose sides are here we have the y-axis, the x-axis, and the line from 0, 4 to 2, 0. So let's write a little formula for the area that we want to maximize. The area of this rectangle, well, I labeled this point xy, so the area is going to be this side times this side. That would be xy. Okay, so that's the area of that red rectangle. And we have to eliminate one of the variables. Okay, so we're going to use the fact that it's inscribed in this particular triangle to get information that'll give us a relationship between x and y. So what we're going to do is we're going to use similar triangles. All right, let me just copy this over. We have the outer triangle, this one, and it has dimensions 4 by 2. And then we have this triangle, this upper triangle over here, above the rectangle. Well, this line is the same as x, so that's one dimension. And what about this height? Well, this height is 4 minus y. Okay, so 4 minus y for the height. Okay, so that's right here. That's 4 minus y. Now, these are similar triangles. They share an angle. They both share this angle up here. And they're both right triangles, so all the angles are the same. Okay, so they're similar. So their sides are proportional. So we have the proportion 4 is to 2 as 4 minus y is to x. Now there's our relationship between x and y. So here we have, let's just reduce that. 2 is equal to 4 minus y over x. And now cross multiply, and we have 2x is equal to 4 minus y, and let's divide by 2, and we have x is equal to 2 minus y over 2. So we could substitute for x 2 minus y over 2, okay, and that will be our eliminate step, and then we'll differentiate a with respect to y. So y will be the variable that's left. All right, so let's look at that here. So we have a is equal to 2 minus y over 2 times y. Okay, so a is equal to 2y minus y squared over 2. Differentiate, and we have 2 minus, and bring down the 2 minus y. And so we get pretty quickly that y is equal to 2. And what is x equal to? Well, let's just substitute. Let's see. We have this equation for x, so we'll substitute, and we get x is equal to 2 minus 2 over 2, or 2 minus 1, or 1. Okay, so y is equal to 2 and x equal 1, and that would maximize the area of this rectangle.